So it's really a great pleasure to be here. My name is Joseph Civic. I'm chairing this session. So welcome to the ELLIS Lightning Talk session at the ICTERI conference. This is a session jointly organized by the ELLIS Associate Unit Lviv and the ELLIS unit in Prague. And it's really a session focusing on presenting and discussing recently published results in machine learning driven fields. And so this is actually a second session. The first session was earlier today, which was an exciting session. And in this afternoon session, we have also a very exciting lineup of 3 speakers. The first speaker is Michal Neoral, who is a PhD student at the Czech Technical University in Prague at the Faculty of Electrical Engineering at the Center of Machine Perception. He's an expert on visual tracking, and he's going to tell us more about his recent work on long-term tracking of every pixel. His work was published at VACVI, which is IEEE CVF Winter Conference on Applications of Computer Vision, and it was published, I think, this year. So, Michal, it's great to have you here, and I'm really eager to learn about your exciting work. The stage is yours. Thank you very much for joining us.
Thank you. Thank you for the introduction, and thank you for the opportunity to present at the Lightning Talks. I would like to also thanks to my colleagues Jonas Scherich and Jiří Matas, which are co-authors of the MFT paper. So this presentation is focused on a specific topic, which is a long-term pixel tracking, which is currently very hot topic and in interest of the biggest AI research teams in the world. So let's start with a brief introduction to some key computer vision terms to help everyone, including these outside this discipline, better understand the rest of the presentation. So let's start. In essence, the feature matching task or correspondence estimation means that for a point in one image, you want to find a correspondence position in another image. Typically, feature matching methods estimate the position for a small number of points, significantly fewer than the total number of pixels in the image. So next level of this is optical flow, which has a task of estimating correspondences, but for all pixels from a reference frame to a target frame. However, this estimation is, as I said, performed only between 2 consecutive images, and optical flows are trained for small changes in images, typically at least. So on the other hand, long-term pixel tracking is not limited by the number of frames, and it estimates not only the position from initial frame to last frame or target frame, but also the positions for all intermediate frames, and moreover, it also determines whenever the points remains visible in specific frames. So we are doing that one. So let's start with a paper. So our paper deals with visual tracking, long-term visual tracking. Standard visual object trackers tracked an object from the first video frame throughout the video using a bounding box or a segmentation mask representation. As you could see in the previous presentations. Applications like structure from motion or video editing benefits from long-term dense correspondences. So optical flow methods output dense correspondences, as I said, however, only between pair of frames. And our method called MFT, which stands for multi-flow long-term tracker, extends this optical flow to dense long-term trajectories over the whole video sequence. So for each point in the first frame, MFT outputs the points and visibility positions and visibility in every other frame of the input video. So a baseline approach for this is simply to chain optical flow fields computed in consecutive frames or between consecutive frames. This is a toy example of that chaining, and the x-axis represents the number of frames or frame number, and the y-axis is the position of a tracked point. For simplicity, the diagram shows just one-dimensional case. As shown in the video, such approach cannot recover from temporary occlusion. Even if the pixel is occluded for one frame, this approach cannot recover from that. And even for non-occluded areas, small errors in optical flow can accumulate over time, which leads to a significant drift from actual position. So another baseline, or another approach, is to estimate optical flow directly between a reference frame and target frame or a current frame. So this way, the optical flow errors does not accumulate. And since the estimation is done independently for each target frame, the direct matching approach can recover after failure. So failure images are just skipped. However, the direct matching is harder task due to a change of viewpoint, change of illumination, and large motion accumulated over time. So in the video, there is a failure caused by a significant camera rotation and its recovery of matching on later frames. Okay, apart from the simple chain of optical flows and the direct matching, there are other possibilities. For example, the target point could be tracked for 2 frames, and then followed by optical flow from frame 2 to frame 5, followed by another simple chaining. This could be beneficial in some cases. For example, if the frames 3 or 4 are occluded, or there are some other difficulties like motion blur, which caused inaccuracy of optical flow in these frames. But this is not the only option. There are some other options which could be possible too. So number of possible chains grows fast with the increasing number of frames in the video. Note that the best tracking result could be achieved using a different chaining scheme for each query point. So each query point could have a different trajectory or different skipping over some frames. Now I will describe our MFT method, which significantly reduces the number of considered chains and selects the most reliable one. So let's go over MFT tracking example frame by frame. So the MFT selects the simple optical flow to the first frame because there are no other candidates. But in a second frame, there are 2 flow chain options. The first one is matching directly from reference frame to current frame. And the second one is computing the optical flow between frame number 1 and frame number 2 and chain it with results from frame number 1. So there are 2 correspondence candidates. And MFT selects the most reliable one according to the strategy I will describe in a moment. Any other candidates are discarded. So in the third frame, MFT considers 3 chaining options. The results on a previous frame chained with the optical flow between frame number 2 and 3. The results on a frame number 1 chained with a direct match from frame number 1 to number 3 or current frame, and direct match. Again, MFT selects the most reliable candidate. This is repeated on each frame of the video. MFT only uses flows spanning 1, 2, 4, and direct match. This selection of logarithmically spaced optical flows or skips significantly reduce the computational cost, making MFT fast. Yeah, and again, the whole procedure is done independently for each tracked points. So each tracked points can have different frames, which is, or the trajectory can have different frames, which is constructed. Okay. So how to select the most reliable candidate? So we estimate uncertainty of each optical flow vector and select the candidate chain with the lowest overall uncertainty. To compute the overall uncertainty, we sum the uncertainties of all flows in the chain. Nowadays, typical optical flow methods extract features from both input images and construct a correlation cost volume, which is then used as the input to the optical flow regression head. In MFT, we extend this with a small uncertainty estimation CNN, which output an uncertainty score for each optical flow vector. We train our uncertainty head on optical flow data sets using a pretty standard uncertainty loss. So during training, the network can balance a high error of the optical flow by predicting a high uncertainty score sigma. However, to avoid zeroing out the loss by predicting high sigma everywhere, the loss contains a regularization term. So standard optical flow methods are trained to work even in occluded regions, which is possible thanks to the surrounding context. In the top right example, the estimated optical flow is correct and has a low estimated uncertainty. But MFT cannot continue tracking this point as it would drift from target point on a head to the occluding bamboo. Because of this, we extend the optical flow network with another small CNN that is trained with binary cross entropy to estimate occlusion maps. In MFT, the candidate flow chains that contained any occluded flow vectors are removed from the candidate pool. Okay, since there is no benchmark for dense tracking, we evaluated MFT on a standard sparse point tracking benchmark called TABWIT. And MFT performed competitively to concurrent work, which are specialized in sparse point tracking while being orders of magnitude faster. The slowest part of the MFT is computation of optical flow. So for application like video editing, the optical flow can be pre-computed, which results in tracking speed of over 100 frames per second and could be used for interactive use. Here's an example of video editing using MFT. So we start with the original video. First, we edit the initial frame of the video, and then we propagate these edits through the entire video using the estimated position outputs from MFT. Here's another example showcasing MFT's capability in handling non-rigid motions. It can handle these motions without restriction on any particular target particle. In this instance, MFT successfully recovers tracking even after a significant occlusion. Okay, I can skip this one. And finally, in our last example, we demonstrate how we change the video style using just a simple example frame of a new style. We then apply this stylized frame throughout the entire video using MFT. So, moreover, MFT can track multiple referenced images. So we are not restricted only for a single reference image. And in this example, the artist created versions of stylized image for 3 referenced images. And we tracked these images throughout the entire video in parallel. We used a normalized uncertainties from individual tracks. The colors correspond to individual tracks. And we use these normalized uncertainties as the blending coefficients to create a stylized version of a video. Note that this output is not intended to be a final version, but rather input for some in-painting algorithms. So another application of dense point tracking is tracking soft tissues during endoscopic operations or endoscopic surgeries. The images displays MFT tracks on surgical tracking dataset. It is worth noting that MFT has been chosen as official baseline by the authors of the Surgical Tracking Challenge. Surgical Tracking Challenge. And so thank you for attention. All raw results and the code, including a simple demo used to generate these videos, are available online. So thank you for attention.
Thank you very much, Michal, for this very nice presentation. Very nice and very impressive work. So we are moving to the question session. We do have some time for questions. So are there any questions in the audience?
Any questions here?
Thank you very much for your talk. And I have a question about certainty quantification method. Yeah, so my just question, why did you decide to use such type of methods like applying CNN to predict variance? Did you try any other ways to quantify uncertainty?
Actually, yes, but I cannot talk about it because we have just a paper in a review. So yeah, so let's say that the newer version do it differently because variance is not very good for estimation. Actually, it doesn't make sense for high errors in optical flows because let's say if the optical flow error is like 30 pixels or more, the matching network, it cannot have this information, like error above certain levels are impossible to estimate as uncertainties. Like if it's something 2 pixels from the correct position, yeah, we can estimate it pretty much correctly. But if it's 300 or 30 pixels, it makes no sense to differentiate between two. So yeah, we tried a lot of different things, but in that paper is this one. No? Yes.
Okay, thanks.
Thank you. So it's just maybe to follow up on this. So it seems that there is some kind of a robust estimator is needed for the errors. Is that you need to have some dealing with outliers is really what is needed in this case?
Yes, that's true. So yeah, maybe choosing the most reliable optical flow based on this, it's, let's say, working pretty much correctly, but the hardest part is estimation of occlusion, so the outliers which are not visible at all. As you can see, for example, on this particular example, the grass look exactly same, or at least for optical flow algorithms, if it's left or right. So when there are a lot of visible points which are correctly estimated, it's fine. But suddenly, when the large portion of the image is occluded, but the newly discovered areas or newly observed areas are very similar to this, the occlusion network has problems to identify if there are outliers in this or not. So
Thank you. Any more questions from the audience?
Yes.
Excellent.
Thank you once again, Michael, for your report. It's very interesting that you managed to track all the points on the image, but can we reduce the computational complexity by using only several specific features instead of all points using this method, or it's inapplicable?
No, it's not applicable because, okay, the other methods do actually tracking of selected points, like hundreds or maybe even less. However, this particular work is based on optical flow or extending optical flow, and optical flow networks estimate correspondences for all pixels in the images. So we cannot choose just a subset. Yeah, we can specify what are target points, and this provide as output, but it doesn't really matter because the method still has to compute all the points.
Indeed, I understand that it has involved like on all the points, but if we need like more interested in one subset of points than the others, for example, to track some specific object, which is hard to distinguish even like for the longer term tracking.
Yeah, you can combine that with some masking. I don't know, for example, SUM2 has pretty interesting results. So you can mask the object and just track, for example, the lioness on this image, and doesn't focus on the background at all. However, the algorithm which we used for computation of optical flow still will compute all pixels or pixels, all correspondences between images. So yeah, you can specify it for subset, but you cannot, at least with this approach, you cannot save a computational time on this. However, as I showed before, we are still significantly faster, like orders of magnitude than the fastest methods available at the time. So it really depends on specific use case.
And maybe just to quickly follow up on this. So this number which you quote on the computational results. So this 2 FPS, this is including optical flow computation. So this is from scratch if you run it on the video.
Yes,
right?
yes.
And if it's computed, it goes up to 100 FPS. That's what it's saying.
That's true. And new version, maybe it will be next month on archive. It's even faster and more precise. So yeah. So this is including optical flow computation.
Okay.
I think that the newer version has better results, and it's like 6 FPS without pre-computation.
Okay, wow. Okay, these are very interesting, very impressive results. So thank you very much, Michal, for joining us today. And thank you.
Thank you for having me. And
thank you very much. I had this very short question, but maybe I'll ask.
Oh, so no, Rostislav, if you have a, please ask. Yeah, I think we can squeeze in one more.
Yeah.
Can you reformulate this approach through considering multimodal particle filters or something like that when you have multiple modes in your probability distributions of possible tracks?
Not sure, but I think we completely skip the probability at all. So now we are not focused on a probability or uncertainties anymore. However, in this approach, yeah, not sure. No.
And maybe
maybe we can move it to offline discussion. But thank you very much.
Thank
Michal.
you.
Thank you.
Much from the Lviv audience. Thank you very much, Michal.
Thank you for all.